H is VH over H. And I can take this and put it back here. Okay. And if I do that, okay, and I also use an additional relation. Okay. What relation am I using here? Let me go back to the figure. This velocity V, okay, which is the velocity of the charge, again relates to the electric field here. And the length, if we think the length of this semiconductor is L, then, and the voltage applied is V, then this electric field here, electric field that is would be in this direction, right? This electric field E is equal to VH, that's the voltage produced, divided by L. Because in a linear conductor like this, all these linear relationships are true. And they come actually from Poisson's equation in electromagnetics. So again, the electric field by the battery across the semiconductor is given by, sorry, this is not the whole voltage. I made a mistake here. It is, this should be, this should be just H, right? Not VH. I used VH. It should be just the applied potential, which is V across these two faces here, because it's V from the battery. So it's V over L. So if I use for E V over L, and I know that V, the velocity, Vn, okay, Vn is actually mu n, that's the mobility, times the electric field. But then the electric field is actually VL. Then I immediately see that I have this relation here. Vn is mu n over VL. So again, I can take this relation and put it back here for Vn. So if I use EH from here and I use Vn from here, you immediately see a very important relation here, which is the mobility, an expression for the mobility of the electrons in this semiconductor. It is the length of the semiconductor divided by the width of the semiconductor H multiplied by the whole voltage VH divided by the voltage applied from the battery multiplied by 1 divided by magnetic field. So that provides me of an experiment or a way to figure out the mobility, work out the mobility from a simple Hall effect experiment. I just take a piece of an N-type semiconductor, put it in it, apply voltage to it, pass a current through it, put it in a magnetic field, measure the magnetic field, and measure VH, the whole voltage. And repeat this for different values of the magnetic field and measure different values of VH for maybe the same value of V. So V is constant, VH change with changing B, okay? And then plot VH and B maybe, and then extract mu n, the mobility. So in many cases, if you notice in the past, I gave you values for the mobility of electrons and mobilities of holes in a semiconductor. Now, these values, where did we get these values from? We got those values from experiments such as Hall effect experiment. And you can see that it's a very useful experiment here because it tells us how to find the mobility. Not only that, you can go further and then use the same relations like this one, which we thought is mu n here. Okay, mu is missing here. This doesn't show Greek letters for some reason. So if you use Vn for mu n V over L, okay, And we use the magnitude of Jn for an electron drift current, we can actually find even relationships like this. The concentration of electrons from the same relation, the concentration of electrons in the N-type semiconductor from the magnetic field, the drift current in the sample, and h, the width of the sample, and the measured hole voltage. So that's another experiment which you can also use. You can vary the magnetic field, okay, and vary the current Jn, okay, and then measure VH. And you can use these relations to extract N, the density of free electrons in the N type. So again, a Hall effect experiment can help us determine the density of carriers in a semiconductor, which is again very, very useful. Okay, so writing, the above equations, you can always, change this formula and have VH, extract a relation for VH. So these are the relations which you can get for VH. And this factor here, 1 over NE, where N is the density of free electrons, E is the electronic charge. Now, this prefactor, 1 over NE, which lump together RH, RH is called the Hall coefficient. So the Hall coefficient for any semiconductor with a certain concentration of free carriers, it has a specific Hall coefficient, R sub H. And this Hall coefficient is 1 over the density of free carriers times the charge, okay, of each carrier. Similarly, we can have a p-type semiconductor. We don't need to have an n-type semiconductor. And again, the analysis is exactly the same. And so if you go through the same kind of analysis, again, we produce the same kind of results. An expression for the mobility of holes on the p-type. You see that here you have u mu sub p, p for holes. And then you also get expressions for the potential, in terms of the Hall coefficient. And now the Hall coefficient has P, which is the density of free holes in the p-type semiconductor. So P is the density of holes, and therefore, again, a p-type semiconductor has a Hall coefficient which depends on the density of free holes. So let's conclude by doing a quick example, maybe an experiment here. A whole sample is biased as shown. See here? And we're passing 10 milliamp current. So this is a current generator, which is the same, same thing as, current generator generates current, but if you want to generate current, you have to have a voltage or a potential difference, and therefore, so a current generator and a bias source more or less produce the same effect on a semiconductor piece. So here we have the semiconductor piece, and here we have the current generator pushing a current across these two faces. Okay, so the current is from here to here, and this is placed in a magnetic field. The magnetic field is 1 Weber per meter squared. Weber is the unit for a magnetic field, the MKS unit, okay, per meter squared. So magnetic field B is measured as density of magnetic flux. So density meaning magnetic flux per unit area. So that's why meter squared. If the charge carriers in the sample are electrons, so this is an n-type semiconductor, what will be the direction of the whole field? Okay, so that's the first question. So let's see, using the right-hand rule for V and B and the force, we see from the figure that the negatively charged electrons tend to be deflected in the negative z direction. The reason I jumped and read the answer because I'm not given, the direction of the magnetic field. So let's see. Along the positive axis. Okay, so the magnetic field is applied along the positive axis. So the magnetic field is in this direction here. So along the positive axis, meaning that on this plane of paper, I can show the magnetic field as a cross. Remember, a cross meaning it's the tail of an arrow. So the arrow is going into the paper, okay? And the tail is facing you, okay? So we use the right hand rule, which is similar, to what we did before. So from the figure, the negatively charged electrons tend to be deflected in the negative z direction. So let's see that if we want to apply the right hand rule for a charge, okay, for a positive charge. So the meaning that, the positive charge, if we hold our hand, so the motion of the positive charge is in this direction, of course, v, okay, that is the positive charge, moves in this direction. And the negative charge moves in the opposite direction, of course, right? So the positive charge moves in this direction, and the positive and negative charge moves in the negative direction. So let's say we want to determine, the deflection in this case. So what we're saying here is that the positive charge will be deflected down here, or the negative charge will be deflected down here from the right hand rule. And remember, when you get the negative charge, you have a minus sign in Lorentz force. And of course, the top will remain to be then positive, right? The top part will be positive. And therefore, you will get a whole field in this direction, EH. Okay? So this is what we get for a whole field. Okay? So apparently, the second question is, the magnitude of the whole voltage VZ is measured to be 10 millivolts. Evaluate the free electron concentration N in the material. And so we use this formula. We know the applied magnetic field. We know H, the dimensions, right? That's the width of the semiconductor. We know the current coming from the current source. And now we know VH, the measured whole voltage. So this is B, this is G, or J is the current, and the current source here, it's 10 milliamps. And we know the area here, the area of this to get J. So we need to have these dimensions. And we have the dimensions here, 10 millimeter, and what's this other one? 10 millimeter, and this one, I can't clearly see it, but you can see it here. 10 millimeter and 1 micrometer. So this is 1 micrometer, this is 10 millimeter, so we can get this area. So the total current is 10 milliamps, and the area is 10 millimeter by 1 micrometer. So that is exactly what we have here. 10 milliamps divided by 1 micrometer times 10 millimeters. Oh, everything is in meter here. So the current density J is in amperes per meter squared. This is consistent with B in Weber per meter squared. And then H, which is the width, right? And let's see, we have it here as 1 micrometer, right? So that is 1 times 10 to minus 6 meter. divided by E, the electronic charge, 1.6 times 10 to minus 19 coulomb, multiplied by the voltage, the whole voltage. We're told that it's 10 millivolts, so it's 10 times 10 to minus 3 volts. And then when you plug in all this, you get N equals 0.625 times 10 to 21 per meter cubed. Okay, right? And then, I guess, the second question, for the small hole voltage VZ in the above, find the electromobility, mu(n). Okay, and again, we drive this formula here, mu n. You go back and look at it, you'll see that mu n is L VH over H VB. So we just substitute. Okay, so our mu n will be equal to, this is L, the length of the semiconductor, which is again given. Where is it given? I'm trying to see. It's not shown in here in the figure clearly, but what we have here, it's about well, L is 5 times 10 to minus 2 meters, so it is maybe uh, 50 centimeters, okay, or 50 millimeters, right? So 50 millimeters, it's 5 times 10 to minus 2 meters, times VH, this is the voltage, the whole voltage, which is 10 millivolts, divided by H, the width, which is 1 micrometer, times V, 10 volts, right? And 1, the Weber per meter squared. Okay, and that gives us a mobility which is equal to 50 meters squared volt minus 1 second minus 1. So essentially that we can use a Hall effect experiment to determine the mobility and the free carrier density in a semiconductor. So this is, the first part, just to conclude, drift in an electric field first, and then drift in a combined electric field and a magnetic field, and the Hall effect. So I'll